Hello friends, in this lesson I will explain the concepts of AC and DC in detail that everyone who is new to learning electrical electronics should know. In this lesson you will be able to find answers to many of your questions and you will have access to a lot of information about AC and DC concepts by the end of the lesson. First of all, where do the DC and AC concepts come from and who invented them? Let's start with that. Thomas Edison, born in 1847, is known as the inventor of the light bulb and the direct current that he used to light the bulb. Direct current is used with the abbreviation DC, which is the initials of direct current. Nikola Tesla, born in 1856, is known as the inventor of alternating current. Alternating current is also used with the abbreviation AC. Since the two inventors lived in almost the same period, DC and AC superiority struggles took place between Edison and Tesla, and this sweet scientific battle still continues today. The struggle for supremacy between Edison's direct current and Tesla's alternating current has divided people into two. While AC and DC struggles continue, let's look at what DC and AC are. First of all, let's look at how DC and AC are shown in the circuit. You can see the DC circuit symbols on the left and the AC circuit symbols on the right. AC and DC sources are commonly shown in these figures in the circuit diagrams. Well, what are DC and AC measurements made with? You can see a multimeter on the left and oscilloscope on the right. While DC measurements are usually made with a multimeter, oscilloscopes are used in AC measurements where we can see the shape of the signal on the screen. When we measure the voltage value of DC power sources with a multimeter, we see a value whose direction does not change in time. For example, we can show the voltage time graph of a 1.5 volts battery like this. We can show the voltage time graph of a 9 volts battery as a constant 9 volts in this way. Therefore, we can say that DC is a current that does not change direction in time. When we measure the voltage value of AC sources with an oscilloscope, we can see a sinusoidal wave whose direction and intensity changes constantly in time, as is the case here. Sometimes it can be confused whether a waveform is AC or DC. For example, the voltage value you see here is a direct current. The intensity has changed. It is an irregular direct current. However, its direction has not changed and has always remained positive. That is, the intensity of the direct current can vary, but its direction must not change at all. On the other hand, the figure you see is an example of direct current. Here, the intensity is constant, but its direction is negative. In other words, since it's always negative and its direction does not change, this is an example of direct current. The shape here is alternating current in the form of sinusoidal wave. The direction has been positive and negative. At the same time, the intensity has also changed. This may not always be the case with AC. For instance, this also is an example of alternating current in the form of triangular wave. It's an example of alternating current as its direction and intensity change constantly in time. Now let's look at how does this alternating current come to our homes. First of all, voltage is produced in the power plant with the help of generators. Then this voltage is converted to high voltage with the help of transformers. The purpose of converting to high voltages to reduce losses in wires between cities while the voltage is being carried. Then this high voltage is carried across transfer stations to city entrances. High voltage is reduced with the help of transformers again at the city entrances. Now this reduced voltage comes to our homes as 120 volts or 230 volts. This voltage value differs from country to country. While it is 120 volts in America, it's 230 volts in Europe and many other countries. This is how we can use this AC produced from our sockets. It basically goes through these stages until it comes to our house from the power plant. After coming to our house, we can now use this AC in our electronic devices in this way or by converting it to DC with chargers. In DC sources, the positive and negative pins of the source are always constant. In other words, its direction does not change in time. For example, let's connect a 9 volts DC source to the lamp as in here. The current will flow from the positive pin of the DC source to the negative pin. Our lamp will light up with this current. The voltage given by this source to the lamp will always be constant at 9 volts. Therefore, the lamp will light with the same brightness. The voltage time graph of this DC source is as you can see on the right. This is how we can show on the graph that it always gives a constant 9 volts voltage. However, in alternating current, the direction of the source and the intensity of the voltage are constantly variable. It's not always constant. In other words, its direction and intensity change continuously in time. We can explain this through the same example again. This time, let's use an AC power supply as the power source. The voltage time graph of this AC source is given on the right. The voltage is in the form of a sinusoidal wave as in our city network. So how do we interpret this graph? When we look at this point on the graph, we can see that the voltage value is 0 volt. Therefore, our lamp will not light at this point as no current flows through the circuit. When we look at this point, we can see that the voltage value has increased slightly. So, our lamp will give some light. At this point, at the peak, we see that the voltage value is maximum. It will also give maximum light at the peak. If we continue, the brightness will decrease at this point. When it reaches this point, the voltage will be 0 again and the lamp will not light. If we continue, the direction of the current will change, this time in the negative part. At this point, the lamp will again give off some light. At the negative peak, it will reach again to maximum brightness. If we continue, the brightness will decrease again at this point. When it reaches this point, the voltage will be 0 again and the lamp will turn off. This is how the direction of the current is constantly changing as positive and negative in AC voltage. The intensity of the voltage also changes constantly between 0 and maximum. We might have a question like this. We use AC atom, so the incandescent lamps we use atom flashes in this way. Yes, that's exactly how it happens, but we can't notice it with our eyes because the flashes are so fast. In the USA, the frequency value of the voltage we use at home is 60 Hz. This means that our lamp blinks 120 times per second. However, our eyes cannot detect more than 20 flashes per second. For European countries, the frequency is 50 Hz. In alternating current, this sinusoidal wave has many parameters such as period, frequency, effective value. To avoid making this lesson too long and boring, I will explain them in the next lesson. Alternating current has some advantages over direct current. In alternating current, the voltage value can be easily increased or decreased with the help of transformers, which consist of coil windings. The voltage value is increased or decreased according to the ratio of the windings at the input and the output of the transformer. In the internal structure of the transformer, we see here, since there are many windings at the input and few at the output, we can say that the voltage value of the sinusoidal wave at the input is reduced at the output. If we do the opposite, we will increase the input voltage. But in the direct current, it is very difficult to obtain very high voltages by increasing the voltage value. Transformers simply step up and down AC. Of course, larger transformers are used to achieve much higher voltages. Very high voltages cannot be generated in DC. It's obligatory to use thick section cables in the distribution of this obtained direct current to the receivers. But since the voltage value is high in AC, the current value is very low compared to direct current. For this reason, thin section cables are used in AC networks compared to DC. If the electricity carried from the power plant to the cities was not AC but lower DC, these cables should have been much thicker rather than the thinner like this. Because we can easily convert AC to high voltages with transformers and carry it with thinner cables. But very high voltages are difficult to achieve with DC. In addition, alternating current motors are lighter and more efficient than the direct current motors. It's easier to take much more efficient and maintenance-free AC motors in small sizes. Therefore, while the use of AC motors is preferred in industrial areas, DC motors are used in applications where smaller power is required. Alternating current can be easily converted to direct current with the help of adapters made with basic electronic circuit elements such as diodes, capacitors, and regulators. However, converting direct current to alternating current is a very difficult process with high losses. Special devices are required. As you can see, the alternating current has many advantages over the direct current. Well, doesn't AC have any disadvantage? The most important disadvantage of AC compared to DC is that it cannot be stored. While DC can be stored with the help of sources such as accumulator, battery, and cell battery, AC cannot be stored. It's used as it is produced. We have discussed the concepts of AC and DC so far. This is the end of our lesson. I hope it was helpful and you liked it. Hope to see you in our next lesson. Thank you and goodbye.